Hello, welcome everyone. In today's lecture, we are going to learn a new concept, which is actually a fairly simple concept, which is the concept of octahedral stress. Okay. So essentially at the end of this lecture, you will understand what octahedral stresses are, and you will be able to calculate the octahedral normal stress and the octahedral shear stress. Okay. So what are these octahedral planes that we talk about? Okay. So if you think of, again, a stress at a particular point, okay, and you know that the principal directions of that particular at that particular point are x, y, and z. Again, we use different notations. In this case, I'm just using this capital X, capital Y, and capital Z as the three principal directions. But these are no different from like the OP1, OP2, OP3, or O1, O2, O3 that we have looked at before. Okay, so essentially, these are just different notations. Essentially, the principal directions in this case are denoted by the capital X, capital Y, and capital Z coordinate system. Okay. If you know what the principal directions are, so what I mean by that, again, I want to emphasize is that you have a point, okay, and then you draw a cube around that point, okay, and on the faces of this cube, you have only normal stresses. You have zero shear stress. So those planes are the principal planes, and the normals to that plane are the x, y, and z direction. Okay, that is what you're looking at. Okay, so if you know what this x, y, and z directions are, essentially what the principal directions are in that particular point, then you can define a family of planes, okay, whose normal satisfy the condition that L square plus m square plus n square equal to 1 over 3. What does actually mean? It essentially means this is a plane that goes through the points 0, 0, 1, 0, 1, 0, and 1, 0, 0. So essentially these planes intersect the x, y, and z axis, which essentially are the principal directions, at unity. Okay, so now you can think of this plane here, okay. That is one of these planes that will satisfy this condition. You can think of another plane that will also satisfy this condition. Okay, I'm just giving an example where you go through that point, which is 0, 0, 1, and this point, this is 0, 1, 0, 0, 1, 0, 0, and this is 0, 0, 1. Okay, the plane passes through both these points. But then, instead of intersecting the y-axis at positive 1, it can intersect the y-axis at negative 1. Okay, so this will be the plane now. Okay, so that is another octahedral plane. That also satisfies the condition that L square plus m square plus n square equal to 1 over 3. So essentially, if you look at the direct and cosines, they basically have values of plus or minus 1 over square root of 3, plus or minus 1 over square root of 3 for m, and plus or minus square root of 1 over 3, or 1 over square root of 3 for n. So if you look at the combinations, so you can have two possible values for L, two possible values for m, and two possible values for n. So essentially, you have 8 combinations because it's 2 cubed. Okay, so that's why you have this 8 planes. So again, you can think of a plane like this. You can think of a plane that is on the opposite side. Okay, where essentially it's going to be not 1, 0, 0 and 0, 0, 1, but rather minus 1, 0, 0 and 0, 0, minus 1. And you can have y to be either 0, 1, 0 or 0, minus 1, 0. Okay, so essentially you can easily imagine that there are 8 possible combinations of this L, M, and N, and each one corresponds to a different plane. That's where the word octa comes from. Okay, octa is 8, right? So you have essentially, you form an octahedron with these octahedral planes. Okay. The main thing about these planes is that they essentially make the same angles or the equal angles with respect to the principal stress directions x, y, and z. Okay, so 2 things to think about. There are 8 of these planes, okay, and all these planes basically have the same angles with respect to the x, y, and z axis, which are essentially the principal directions. Okay. Now, what is special about these planes? Why are we actually looking at these specific planes rather than some other arbitrary plane? The reason that we are interested in these octahedral planes is because the shear stresses in these octahedral planes actually help us figure out whether a material is going to yield or not, whether it's going to plastically deform or not. Okay? This is especially true for ductile materials like metals. So essentially, if you are given the stress rate at a point in a metal, okay, and you want to figure whether this metal is going to actually plastically deform or yield, what you do is you calculate the octahedral shear stress at that particular point. Okay? And if the octahedral shear stress at that particular point exceeds a particular threshold, then it's likely that the metal will yield at that particular point, or it will start to deform plastically at that particular point. So these octahedral shear stresses especially are particularly important to figure out whether some material is going to yield or break or fail and so on. Okay? And that is the reason why we look at specific planes like the octahedral planes and figure out whether the shear stresses on them exceed a particular threshold or not. Okay? We will get to this a little bit later when we look at failure theories for ductile and brittle materials. Okay? But I just wanted to give you an idea of why we are doing this here. Okay? Now, what is special about this octahedral planes is also that the normal stress as well as the shear stress, okay, on each one of these planes are identical. Okay? The normal stress on this octahedral planes is given by sigma octahedral, okay? And that is nothing but the average of the principal stresses. Okay? Sigma 1 plus sigma 2 plus sigma 3 divided by 3, which is nothing but 1 over 3 times I1, which is the first stress invariant. Okay? Because I1 is sigma 1 plus sigma 2 plus sigma 3. So all these 8 planes, okay, have the exact same normal stress. Okay? And the shear stress on all these 8 planes are also identical in magnitude. Okay? And that is given by this expression here. Okay? So you can write it either in terms of the invariance I1 and I2, or in terms of the principal stresses sigma 1, sigma 2, and sigma 3. Okay? You can write it in either way. They are equivalent expressions. Okay? But the main thing to notice that sigma octahedral and tau octahedral are essentially the same on all these 8 planes. Okay. So here you might ask a question, why do you specify only one shear stress? Okay. Usually when you look at a plane, you look at an x plane, for example, you have tau xy and tau xz. Now here we have only tau octahedral. So what that actually means is that it is a resultant shear stress in that plane. So if you think of a plane like this, okay, and you have a shear stress, say tau 1, or let's just make this tau xy and say that is tau xz, and the normal to the plane is the x direction, then that is tau, and that is nothing but square root of tau xy square plus tau xz square. Okay? So this is the octahedral shear stress that I'm talking about. Okay? So that is the resultant shear stress, okay, on the plane. Okay? And that is equal to this value, tau octahedral. So if you can think of these octahedral planes, you have a normal stress which is perpendicular to the plane and a shear stress that is acting along the plane. Okay? And the normal stress is sigma octahedral and the shear stress is tau octahedral. And both these values are essentially the same for all these 8 planes. Okay? So now this is the way to calculate sigma octahedral and tau octahedral if you already know what the principal stresses are. Okay? If you don't know the principal stresses, you are just given the stress matrix and an arbitrary coordinate system at a particular point, you can still calculate what the octahedral shear stresses are, both the sigma octahedral and tau octahedral, and that you calculate using these 2 expressions. Okay? So sigma octahedral is nothing but the average of the normal stresses, sigma x plus sigma y plus sigma z divided by 3. And tau octahedral has a somewhat more complicated expression, but once you know the stress matrix and you know sigma x, sigma y, sigma z, and tau xy, tau yz, and tau xz, you can essentially calculate what tau octahedral is. Okay? And the reason, as I told you, why we calculate these quantities, especially tau octahedral, is because they will help you determine whether a material is going to yield or not at a particular point, especially for ductile materials. Okay? So with that, I will conclude this class and I'll see you in the next lecture. Thank you.